apply Blankinship'S method, an algorithm to find the greatest common divisor of two integers a and b. The problem is to find the greatest common divisor of two integers a and b. And the first step is to form this matrix. It's a 2 by 3 matrix because it has 2 rows and 3 columns. Column 1, 2, 3. So the shape of this matrix is 2 by 3. And from your course in linear algebra, a matrix is a rectangular array of numbers. And the shape or size of the matrix is given by the number of rows and the number of columns. And this matrix has 2 rows, row 1 and row 2. And it has 3 columns, 1, 2, 3. So the size or shape of this matrix is 2 by 3. After we form this matrix, we transform this matrix into an equivalent matrix by using elementary row operations of this form. The objective is to make this entry here B, to make that B equal to transform it to 0. And once you have 0 in this entry, the algorithm is complete. That means you have found the greatest common divisors of A and B, and denoted by D, it is the entry here in the first row, first column. And to check if that is correct, we use bisous lemma that says this greatest common divisor D is a linear combination of the integers A and B, where in bisous lemma, S now is equal to y1, the entry in the first row, second column, and T in our discussion earlier is equal to y2, the entry in the first row, third column. We take an example, we find the greatest common divisor of 35 and 15. This means the integer A is 35 and the integer B is 15. And we write this matrix 2 by 3 matrix with first column A and B, 35, 15. Second column, entries are fixed 1 and 0. Third column, entries are fixed 0 and 1. And we will transform this matrix in a matrix of this form. If after using the elementary operations you do not get this a matrix of this form, then you have to apply again the following steps. We start with 35. We write 35 as we apply the division algorithm to 35. We divide 35 by 15, and you get 2 point something. You get only the whole number part of the quotient, that is 2. 15 multiplied by 2. And we should add a constant here to maintain the equality. 15 multiplied by 2 is 30. Subtract 30 from 15 and you get 5. So we must add 5 here. To keep the equality sign, you get 35 equals 35. And now, transpose, the remainder 5 must be at one side of the equation only. So we transpose 15 times 2 to the left hand side. But instead of writing minus 15, we write plus 15 multiplied by minus 2. We have 35. Transpose 15 times 2 to the left hand side, you write plus 15 multiplied by minus 2. is equal to 5. When you transpose, instead of writing the negative sign before minus 15, you write the negative sign in the second factor, 2. And you write here positive, and positive times negative is negative. Now we replace the entries of the first row using this elementary row operation. R1. We replace the entries of R1 by multiplying the entries of row 2 by negative 2. Negative 2 multiplied by R2 plus R1. And perform this operation. We have minus 2 multiplied by R2, 1501 plus R1. Entries of row 1, 35, 1, 0. To perform this operation, multiply each entry of row 2, 15, 0, and 1 multiplied by negative. It's called elementary operation because we are now operating on a row. We are multiplying each entry of a row by a constant. So negative 2 times 15 is negative 30. Negative 2 by 0 is 0. Negative 2 by 1 is negative 2. Plus the entries of row 1, 35, 1, 0. And the new entries of row 1, negative 30 plus 35 is 5. 0 plus 1 is 1. Negative 2 plus 0 is negative 2. And the equivalent matrix has entries in the first row, 5, 1, negative 2. And the entries of the second row, the same as is 15, 0, 1. And this is the first step in Blankinship'S method. We replace the entries of row 1 with the new entries by performing these operations. Now we replace the entries of row 2. We divide 15 by 5. And 15 is exactly divisible by 5. 15 divided by 5 is 3. This means that there is no remainder, or the remainder is 0 when we divide 15 by 5. Unlike here, when we divide 35 by 15, there is a remainder of 5. Again, we should have only the remainder at one side of the equation. So we transpose 5 times 3 to the left-hand side. But instead of writing minus 5 times 3, we write plus 5 times quantity, negative 3. We have 15. Transpose to the left-hand side, you get plus 5 multiplied by minus 3. Equals 0. And minus 3 now is the constant we will use to generate the new entries of row 2. we generate the new entries of row 2 by multiplying this constant negative 3 by row 1. Plus row 2. And we perform these operation, multiply negative 3 by the entries of row 1. Entries of row 1 are 5, 1, negative 2. Plus the entries of row 2, 15, 0, 1. And multiply each of these entries by negative 3. Negative 3 by 5 is negative 15. Negative 3 by 1 is negative 3. Negative 3 by negative 2 is positive 6. Plus the entries 15, 0, 1. And we add negative 15 plus 15 is 0. Negative 3 plus 0 is negative 3. And 6 plus 1 is 7. We now write the equivalent matrix. The first row as is, because it is the second row whose entries we now replace. And the new entries of row 2 are 0, negative 3, 7. And you can see that this third matrix is already of this form, where D is equal to 5. And that means the solution is complete. That means you stop and you have already the solution. The greatest common divisor of 35 and 15 is D, and D is equal to 5. The greatest common divisor of 35 and 15 is D, and D is equal to 5. You can check 35 divided by 5 is 7, and 15 divided by 5 is 3. And 5 is the largest positive integer that can divide 35 and 15. And there is another way to check if the solution is correct. If that answer is correct, we apply bisous lemma. This equation must be satisfied. 5 must be equal to y1 a, where y1 is 1, and y2 is negative 2. And by bisous lemma, this must be satisfied. D is 5, and 5 is equal to the linear combination of A and B, where y1 is 1, multiply by A. Our A is 35. Plus y2. y2 is negative 2. multiply by b, and b is 15. We have 5. 1 times 35 is 35. And positive times negative is negative. 2 times 15 is 30. And 5 is equal to 5. Where 5 at the right hand side is the difference between 35 and 30. So our answer 5, the greatest common divisor of 35 and 15, is correct. And you must note that Blankinship'S method for finding the greatest common divisor. Blankinship'S method for finding the greatest common divisor of A and B applies only when A is greater than B and B is greater than 0, which means that A and B are both positive integers and the integer A is greater than B, such as 35 and 15, they are both positive integers and the integer A is greater than B. And this is the condition for which Blankinship'S method will work. We take another example. We now find the greatest common divisor of 1876 and 365 using Blankinship'S method. And in this given, A is 1876. And the integer B is 365. We initially write the matrix with entries in the first column A and B. 1, 8, 7, 6, and 3, 6, 5. Entries in the second column are fixed 1, 0. And entries in the second column are fixed 0, 1. And by elementary operations, we transform this matrix into a matrix of the form B0 in the first column, Y1, X1 in the second column, and Y2, X2 in the third column. And we do that by replacing first the entries of the first row. And to do that, we divide 1876 by 365. Using your calculator, you divide 1876 by 365 and you should get 5.1397, but only take the whole number part of the decimal number, which is 5. And to find the remainder, we subtract this product from 1876. We have 1876 minus 365 multiplied by 5. And you should get 51. And we transpose, the remainder must be the only constant left at one side of the equation. We transpose this product to the left hand side, but we write the negative in 5. So we have 1876 plus 365 multiplied by minus 5 equals 51. Transpose, you get plus 365 multiplied by negative 5 equals 51. And it is this constant negative 5 that we will use to replace the entries of the first row by this elementary operation. We replace R1 with minus 5 multiplied by row 2 plus row 1. We perform this operation. Multiply row 2 by negative 5. Multiply 365 by negative 5, 0 multiplied by negative 5, and 1 multiplied by negative 5. We multiply 365 multiplied by negative 5. We get 1,825 negative. 0 multiplied by negative 5 is 0. 1 multiplied by negative 5 is negative 5. Plus the entries of row 1, 1876, 1, and 0. And the new entries of row 1 are 1876 minus 1851 equal 1876 minus 1825, or negative 1825 plus 1876 equals 51. 0 plus 1 is 1. Negative 5 plus 0 is negative 5. And the equivalent matrix has entries in the first row, 51, 1, negative 5. In the second row, we have 365, 0, 1. Now we replace the entries of the second row. We divide 365 by 51. 365 equals 51. To get the integer here, divide 365 by 51. We have 365 divided by 51. You should get 7.156, but you only take the whole integer part of this decimal number, which is 7. Plus the remainder, which is equal to 365 minus 51 times 7. 365 minus 51 times 7. And we should get 8. Again, we transpose 51 to the left hand side. We have 365. But we write the negative in 7 instead of 51. And we write plus 51 multiplied by negative 7. Equals the remainder 8. And it is minus 7 that we will use to generate the new entries of row 2. We replace row 2 with the new entries by multiplying negative 7 by row 1 plus row 2. Multiply the entries of row 1 by negative 7. These are the entries of row 1. Multiply each of them by negative 7. 51 multiplied by negative 7. We get negative 357. 1 multiplied by negative 7, negative 7. And negative 5 multiplied by negative 7 is 35. Plus the entries of row 2, 36501. And we add negative 357 plus 365 is 8. Negative 7 plus 0 is negative 7. And 35 plus 1 is 36. And these are the entries, the new entries of row 2. And the equivalent matrix. Entries of row 1 as is 51, 1, negative 5. And the new entries of row 2 are 8 minus 7, 36. And you can see that we did not get 0 here. That means the solution is not complete yet. And so we repeat the process by replacing again the first row with new entries. And we do that by dividing 51 by 8. We write 51 equals 8. And to find the number here, divide 51 by 8. You should get 6.375. Again, take only the integer part of this decimal number, 6. Plus the remainder, which is equal to 51 minus 8 times 6, or 51 minus 48. 51 minus 48 is 3. Again, we transpose 8 multiplied by 6 to the left-hand side. We write 51 plus 8 multiplied by minus 6. Is equal to the remainder 3. And we use minus 6 to replace the entries of row 1 by multiplying minus 6 by row 2 plus the elements of row 1. We perform this operation. Minus 6 multiplied by 8. Multiply row 2 by minus 6. This is row 2 multiplied by minus 6. So we have 8 multiplied by minus 6 is minus 48. Negative 7 multiplied by minus 6 is positive 42. And 36 multiplied by negative 6 is 216. Plus row 1, 51, 1, negative 5. And the new entries of row 1, minus 48 plus 51 is 3. 42 plus 1 is 43. And 216 minus 5 is 211. And the equivalent matrix, the new entries of row 1, 3, 43, 211. entries of the second row as is 8 minus 7, 36. Now we replace the entries of row 2. We divide 8 by 3, or we write 8 as 3 multiplied by a positive integer. To get this positive integer, you divide 8 by 3. In your calculator, 8 divided by 3 is 2.666. But you only get the integer part of this decimal number, which is 2. And we find the remainder by subtracting 6 from 8, or 8 minus 3 times 2, or 8 minus 6 is 2. And we transpose 3 times 2 to the left-hand side, so that we only have the remainder 2 at the right-hand side. We have 8. And it is minus 2 that we will use to replace the entries of row 2 by multiplying negative 2 by row 1 plus row 2. We perform this operation, multiply row 1 by negative 2. This is row 1 multiplied by negative 2. 3 multiplied by negative 2 is negative 6. 43 multiplied by negative 2 is negative 86. And 211 multiplied by negative 2 is negative 422. Plus the entries of row 2. Row 2, entries 8 minus 7, 36. And the new entries of row 2 are negative 6 plus 8 is 2. Minus 86 minus 7 is negative 93. And minus 42 plus 36. Minus 422 plus 36 is negative 386. And equivalent matrix elements of row 1 as is 3, 43, 211. And the new entries of row 2, 2, negative 93, negative 386. And you can see that still we do not get a zero entry here. That means we have to repeat the process again by replacing first the entries of row 1. We write 3 as 2 multiplied by a positive integer. And 3 divided by 2 is 1.5. But we only take the integer part of the decimal number 1.5, which is 1. And the remainder is equal to 3 minus 2 multiplied by 1, or 3 minus 2 is 1. Again, we transpose 2 times 1 to the left-hand side, we get 3. 3 plus 2 times negative 1 equals the remainder 1. And we will use negative 1 to replace the entries of row 1 by multiplying row 2 by negative 1. And to negative 1 times row 2, we add row 1. We perform this operation. Multiply the entries of row 2 to negative 3, negative 386 by negative 1. 2 times negative 1 is negative 2. Negative 93 multiplied by negative 1 is positive 93. And negative 386 multiplied by negative 1 is positive 386. And we add the entries of row 1, 3, 43, 211. And we add negative 2 plus 3 is 1. 93 plus 43 is 136. And 386 plus 211 is 597. Now we write the equivalent matrix, the matrix equivalent to this matrix, by replacing row 1 with 1, 136, and 597. Before we write the equivalent matrix, we make some correction in the solution. We have R1 replaced by this elementary operation minus 6 multiplied by row 2 multiplied by R1. Where row 2 here is this row with entries 8, minus 7, and 36. Multiply each of these entries by negative 6. Negative 6 multiplied by 8 is negative 48. Negative 6 multiplied by minus 7 is positive 42. And negative 6 multiplied by 36, that's negative, not positive, negative 216. And so if we add negative 216 minus 5, we have plus, we get negative 221. And these are the new entries of the first row. 343, 343, 343, and negative 221 instead of positive 211. And here we replace row 2 with minus 2 multiplied by row 1. Minus 2 multiplied by row 1, where row 1 has this entry 343 negative 221. We have minus 2 multiplied by 3 is negative 6. Negative 2 multiplied by 43, that's negative 86, correct? And negative 2 multiplied by negative 221, that's positive 442. This should be positive 442. And if we add, minus 6 plus 8 is 2. We have 2. Minus 87, minus 7. Minus 86 plus negative 7 is negative 93. And 442 plus 36, that should be 478 positive. And this should be positive 478. Again, we replace row 1 by this elementary operation. We multiply the entries of row 2 by negative 1. These are the entries of row 2 multiplied by negative 1. 2 times negative 1 is negative 2. Negative 93 multiplied by negative 1 is positive 93. Positive 478 multiplied by negative 1 is negative 478. And this should be negative 478. Plus the entries of row 1. And this should be negative 221. Plus the entries of row 1, we have 3, 43, and negative 221. And we add negative 2 plus 3 is 1. 93 plus 43 is 136. And this should be negative 699. And that's the correction. Again, negative 478 plus negative 221 is negative 699. These are the new entries of row 1. And we write now the equivalent matrix. The matrix equivalent to this matrix, the first row entries are now 1, 136, and negative 699. And the second row entries are as is. Now we find the new entries of row 2, because in here we found the new entries of R1, row 1. Now we generate the new entries of row 2 by dividing 2 by 1, or by writing 2 equals 1. Multiply a positive integer, and 2 divided by 1 is exactly 2. Which means that there is no remainder, or the remainder is 0. Again, we transpose 1 times 2 to the left hand side, and we write plus 1 times negative 2. At the left we have 2. Transpose 1 times 2 to the left, and we write plus 1 times negative 2. Equals the remainder 0. So the constant we will use to generate the new entries of row 2 is negative 2. And the new entries of row 2 are obtained by multiplying negative 2 by row 1. And to this product, we add row 2. Multiply row 1 by negative 2. 1 times negative 2 is negative 2. 136 times negative 2 is negative 136 multiplied by negative 2 is negative 272. And negative 699 multiplied by negative 2, you get positive 1398. And we add the entries of row 2 to minus 93 and positive 478. The new entries of row 2 are 0, and this is negative 365 and 1,398 plus 478 equals 1876. And the equivalent matrix entries in the first row as is 1, 136, and negative 699. And the new entries of row 2 are 0, negative 365, and positive 1876. And you can see that we already have a 0 entry in the second row, first column, which means that the divisor, the greatest common divisor of 1,876 and 365 is 1, which is denoted by D. And we check if our answer is correct by applying bisous lemma that says D is equal to the linear combination of A and B, where A is 1,876 and B is 365. To check, we verify if this equation is satisfied. D is 1. And 1 must be equal to Y1. Y1 is the entry, the first entry in the second column and first row. 136 multiplied by A. Our A is 1,876. Plus Y2. Y2 is the entry in the third column and first row. Negative 699. Multiplied by B. B is 365. We multiply 136 by 1876. And you should get 255, 136. Positive times negative is negative. We multiply 699 by 365. And you should get 255,135. And the difference, 255,136 and 255,135 is 1. Hence, this equation is satisfied. We have shown that the greatest common divisor, 1 of 1,876 and 365, is a linear combination of the integers a and b, where a is 1,876 and b is 365. For y1, for integers y1 equals 136 and integer y2 equals negative 699. For your practice, please try the following exercises. Find number 1, greatest common divisor of 267 and 112. Number 2, find the greatest common divisor of 216 and 135. 3. Find the greatest common divisor of 11,312 and 11,321. And for all of these three numbers, you apply Blankinship'S method. And you check your answer using bisous lemma. And that completes our lesson for today. Thank you for joining me in my class today in number theory. And if you have question about the lesson today, you ask your question in the comments below. And that's the completion of our lesson for today, bisous lemma. And again, this lemma is just an existence theorem, an existence lemma. It does not provide us with a method for finding the greatest common divisors of two integers a and b, as well as the integers m and n that we use to write a and b as linear combinations. But we will use bisous lemma as a check when we apply Blankinship'S method, the algorithm for finding the greatest common divisor of two integers a and b, where a is greater than b and b is greater than 0. Both integers are positive, a and b are both positive, but a is greater than b. If you have a question about the lesson today, please ask your question in the comments below. Thank you for joining me in my class today in number theory.